Thank you for coming tonight. It's a pleasure to introduce Bruno Jedynak, who is an assistant research professor in the Department of Applied Mathematics and Statistics. He got his PhD under the supervision of Don Gieman in France at INRIA in '96. And right now he will talk to us about diffusion kernels and graphs.
Thank you, Damianos. So, last week, Damianos came to me and told me, hey, Bruno, could you speak for the seminar, next week? And I told him I have nothing to say. Well, nothing ready. He told me, but, you gave a speech in AMS, and why don't you redo it? So in AMS, I gave a speech for undergrads. That was, so this is the title of the speech, and so I've modified it slightly, but it's still kind of a presentation that is made for an audience of undergrad, and it has a lot of equations because you're supposed to be able to do everything. But I'm not going to comment everything. But on your side, you should be able to go through each line as I'm speaking about what I'm doing. So I'm going to tell you about diffusion kernels on graph, and actually I'm going to focus on try to build some unigram models. So my talk is organized as follows. So I'm going to tell you about unigram models, and my goal will be to build some new unigram models, and in just a few words, when you do density estimation, one of the very popular and efficient methods is to use kernel estimate, just to smooth using the kernel. Now, what about in the discrete world? How do we define a kernel in the discrete world? So this will be essentially the purpose of my talk, and some experiment on showing the kind of unigram model you can create with that, and just compare them to a standard known solution. So I'm going to tell you about what is the heat equation, just in order to define a diffusion, so over the plane. Then we're going to define it over a graph. Then we're going to apply it to unigram models. Then we're going to see another construction that is called normalized diffusion, and that is not linked to what I know to partial differential equation, as the formalism that I'm going to show you first is. And from that, we're going to build more unigram models, and then I'm going to show you some experiments. So let's get started. So the setting is this one. So we have a closed vocabulary, a set of words, finite, say 100,000 total number of words. And we have a training set of size n. So each one of these are words, and surely they are repetitions. So these are the things that you guys call the tokens often. And so n of x is the number of times the word x has been seen in the training set. And we want to build a probability mass function, we call it pi, over the set of words v. And such a distribution is called a unigram model, so we won't consider any history. So it might be useless, but all right, it might be a starting point. So what do you do to start? What do you do to start? You look at the empirical distribution. So there are two ways to write it, or for each word you look at a set of counts and you normalize it. And you can rewrite it that way. So delta, here in my talk, delta of u is the function that takes value 1 if the property u is true, and take the value 0 if not. So this is what, this is the first thing you think about doing. This is what I teach my students in statistics to do, use maximum likelihood estimator. And this is what you end up, and it has very nice asymptotic justification. However, when we are not in the asymptotic regime, it's not very good. And in particular for words, it turned out that somehow the true distribution of a word is so skewed that even if we have a large training set, we still at a regime which cannot be considered as asymptotic. And moreover, this probability will tend to put zero mass on many words, all the unseen world. And this is a property that is not desirable. One of the reasons is that often this is used as a prior model for doing speech recognition or other kind of things. And if a prior puts zero mass on some state, you will never be able to infer this state. And so that's a very bad thing. So when this thing is not working, what I tell my student is, all right, so maybe look at Bayesian estimate. And so put a prior maybe on the set of distribution of a word. All right, and if you put a Dirichlet prior, you're going to end up with estimator like that. They are called add beta, and there are two formulas here. And let me just comment on this one. So you adjust a constant to the count, to all the count, and you normalize. And this has, if beta is strictly positive, this put a strictly positive mass on every word. But it's not what people that do language modeling use. They use something very different. And this is one of the versions of the tool that they use that I call the good Turing, and it's defined that way. So there is a new function here, R is by J is the number of words observed J time. And so the good Turing is defined that way. So it's so there is one definition for word with small count and another one for word with large count. So this one is just the empirical. If they are large count, just take the empirical. Alpha is set up to normalize things. And M is, I don't know, some value between 5 and 10. And when you look at the empirical result measured by the code length on the testing set, this estimator is incredibly good. And somehow I've learned that, when essentially I arrived and I had, first I start to be interested in this problem, talking with Sanjeev, and I was so surprised that such a strange object could give such great performance. And suddenly what I try to do is try to come up to bring it back to things I know. Maybe I should not. Maybe just something new and just something that should be understood for what it is. And actually there is some work, and very interesting work, to try to justify why the performance of this estimator are good. But I still, and this talk is, one of my goals in studying the theory was to try to see if we cannot understand this thing from a point of view of some maybe more well-known estimator. So let's just look at the right side of that. So that's another way to write the add beta. It's interesting because we see that it's a linear combination between two estimators. So this is pi 0, this is the count, the empirical distribution, and this is the uniform distribution over all the world. And you just do a linear interpolation between the two, and you get all the family of estimator indexed by lambda or beta if you want. And so this reminds us, and I've tried to go in this direction to build some different add beta, saying that, wait, what you do here is essentially you move from one distribution to another one, and you're going to look at this line, and maybe if you have some metric in the space of distribution, this line defines a geodesy. Now, maybe there are some other metrics that are better in the space of distribution, and I've tried things like that and defining different geodesics, so that would not be lines, but that are curves. But actually, I didn't obtain something that of the performance would even approach this good theory. So what I'm going to do today is to try to approach what this estimator is doing by another way. So we're going to look at diffusion. So remember, when you are when we try to estimate the density of a continuous random variable, so you observe some values, and one thing you're going to do is you're going to smooth it. So if you put some bins, you don't even need actually, but all right, you try to smooth it. Okay, let's say you put some bins somewhere, so you get a large value. I don't know, there are some regular bins, and then there are some zeros, and maybe things like that. And then what you're going to do is somehow try to do some smoothing like that. All right? And if your data point is called xi, actually the formula you're going to get is something like some y equal 1 to n, or some function here. So that's going to be your estimator. And this function is called a kernel. Right?
It's an estimator of what?
Of a density of point. If you have a sample of point, x1, xn, you assume they come from some density that is unknown, maybe it's f. Then you build this estimator of f. It's called f hat, and it's called the kernel estimator of f. And there is a lot of work on how to choose this kernel. Should it be data dependent? What should be the size of this kernel? And one of the popular choice is to choose the Gaussian kernel. So it's a Gaussian, and still, so it's centered at 0, but still you have to define what is the standard deviation of this thing. All right, and this kernel, actually it's a solution of the diffusion equation. So kernel, some kernel come from diffusion equation. So my goal is to do the same thing, but in a discrete world. So let's go to what the diffusion is. So the diffusion is, so here is an example. This is a simulation. I start from here, so it's an image. So I'm going to look at diffusion over the plane. So this image is defined over a plane, and think that the gray level here is the value of the function. Okay, so if it was on the floor, you would have the value of the function that is kind of a rod with a certain height. All right. And you start from that, so it has some distribution. It's fairly sharp. There are some big jumps. And then if you diffuse it, you're going to smooth it. And here is the smooth version, and you can see that between here things begin to merge because of the diffusion process. So what is the? So I'm going to go to what is the diffusion. And then I'm going to build unigram model. So there is a parenthesis that should come here. So the idea is going to be like that. We're going to build a graph. The vertices are going to be the set of words. We're going to define what are the edges. Eventually, we're going to put some weight. We're going to start with the empirical. That is, the empirical for each word, think that the temperature is the relative frequency of this word. All right? So you have one value of temperature out of each word. And then we're going to diffuse and stop. All right? And I won't study when to stop, but I want to study that, and so what should be the way we should diffuse. All right, so let's go. So I can comment some of that. So this is, what you see here is the usual diffusion equation. So we write the kernel is the temperature at time t at x when starting at time t equals 0 with the heat concentrate at y. Okay, so all the heat is at y, and we diffuse. And so the diffusion kernel is a solution of a partial differential equation that you see here. So here, in this equation, there are actually only two variables. X, so here it's in R2, so x is a point in R2, or two real numbers, and then there is time, and y is fixed. Okay? So here you have the derivative with respect to time of this function of t and x, and here, and on the right side, you have alpha, which is a coefficient, and this, which is just the Laplacian of this function. And the Laplacian is defined here. Okay? So for any function to be able to solve that, first this should be defined, so it should be a fairly regular function. So and here you have the second derivative, the sum of the second derivative with respect to each variable. And you would extend, you can extend that in R3, R4, R to the power n, just the Laplacian is just the sum of the second derivative with respect to each of the variables. All right. Okay, and it turned out that this equation, if there are no boundary solution, it has a solution which is very simple, which is the Gaussian kernel. That is the density of a random variable, which is normal, center at y, and with a covariance matrix which is proportional to the identity. So everything is isotrope. And let me just remark that alpha here just plays the role of a scale. That is, if you change the way you measure time, then you change your alpha. And another property which is very interesting is that actually if you solve the equation for when you start with all the heat at y, and you get the solution, the kernel, then it's very easily to get the solution for when you start with the heat with a certain density, I should say the temperature, I guess. Oh yeah, got it. You start with a certain density of temperatures that I'll call G of y. So, okay? And then to solve it, you just have to do the convolution, which is here. You see it's a convolution because you multiply by this. All right? And so you have to compute this integral and you get the result. Okay, that's a very desirable property. So we're going to start from that and we're going just to discretize this equation. All right? So let's do that. So I won't follow everything, but so we're going to use a symmetrical derivative. So this is...
No, can you just go back to the previous slide for just 1 minute? So when you write over there the integral, it's the integral with respect to y, right?
Yeah.
And you put 2 signs because you're thinking of y as a 2-dimensional thing.
Yeah, exactly. It's
Okay.
on the plane.
Because it's not, there's no integration with respect to x going on.
No.
Okay, right, good.
So let's discretize the Laplacian. So what I want to do is to define it on a graph. So my time will still be continuous. I'm fine with that. But my space variable, I want it to live on a graph and not on R2. So I'm just discretizing the Laplacian. So I'm using symmetrical derivative. So this is the symmetrical derivative, that is these 2 things are equal when you let h goes to 0 on the right-hand side. So if you use this definition, then you can extend it to define the second derivative. What you do, you take the derivative of the first one, which is what I'm doing here. So I expand. All right. You can, and then I obtain, I regroup the term and I obtain that. So if I do it for the derivative with respect to x2, I obtain certainly the formula here. So, all right, so I'm going to put it back here. So the sum of the 2 derivatives, you have them there. So I'm going to write it in a setup that begins to resemble the setup of graphs. So what goes on? I'm at the point x1, x2, and it's like I had 4 neighbors, all right? So I have x1 plus h, x2, x1 minus h, x2, then I have x1 and x2, say plus h, and I have x1 and x2 minus h. And to compute the Laplacian, it looks like I'm building a graph like that. So I have the neighbors. So I'm going to call mu of x, this set of 4 neighbors, and I'm going to call d of x, the number of them, there are just 4. And I can rewrite the Laplacian like that. So there is this constant here, and what I have to do to compute the Laplacian of function f, I just sum up the value of f at all the neighbors, and I subtract the number of neighbors times the value of the function f at x. Right? So that gives me a notion of a Laplacian, which is nice actually. It converges. If I let my edge go to 0, it's going to converge to a true Laplacian. But now I'm just going to use it as is, as the definition of a Laplacian of our graph. All right. So let's have a non-oriented graph. So there is a finite set of vertices. There is a set of edges. We're going to write like that, x with a sign like that, y, when 2 vertices have an edge. And we're going to assume that there is no edge from a vertex to itself. And it's not oriented. So now, it's just a simple graph. And I don't even need that it's connected. Also, after I will speak about some properties that will need the fact that it's in one piece. All right, we define the degree, which is just the number of neighbors. So remember, there is neighbor something like that. this construction. In the next construction, actually, we'll have things like that. And a function, look at the function from V to R. So you can look at it as a function or as a vector, because it's just given by the list of the value it takes. And if you look at the function that take two vertices and give you a real value, you can also look at that as a n by n matrix if the number of vertices is n. Okay, so let's define the Laplacian. So we start with what we have. All right. So I choose h equal 1. You remember that h plays the role of the alpha in the continuous version. So it's just a scale in time. So I can take h equal 1 and that give me some unit of time. So this is the definition of the Laplacian, and I'm just going to rewrite it so you can follow this. So I use delta of x is the neighbor of y, which is the function that take the value 1 if this is true, 0 if not, so that I have a sum of everywhere. And here I introduce the function delta of x equal y, same thing to have a sum everywhere. Then I can put f outside, and I can rewrite it like that, and you recognize the product of a matrix times a vector. Right? So the Laplacian is just h times f. The Laplacian of a function f is h times f, and so it's you can look h as an operator. It's which is like that. So it's a difference of two matrices, A, which is the adjacency matrix of G, and D, which is the degree matrix of the graph, which is the diagonal matrix with each entry on the diagonal is just the number of vertices. So it's a diagonal matrix. Okay, so now that we have defined the Laplacian, we are ready to define the heat equation of a graph. So we're going to take two vertices and time, which is still going to be continuous and positive, and we're going to define kt at xy as the temperature at x at time t, when starting with the unit temperature at y at time 0. All right, what is k0 of xy? By definition, it should be just 1 if x equal y and 0 if not. So k0 matrix term is just the identity. And so we define the heat equation exactly the way was defined the heat equation in the continuum. That is, so y is fixed, and same thing is it's going to be now actually a simple differential equation. So there is x, we want that for each vertex x, and for each time, and for each instant, we want to have this following. Now, it's just a system of differential equation. This is just a linear operator on the right-hand side, and on the left-hand side, it's just the derivative of this operator. So before I give you the solution of this linear differential equation, let's just look at what it's doing. So let's fix y, and so let's not ut of x, this quantity, so we can expand it. So the left-hand side, I just keep it, I just expand the right-hand side. So it can give me, so this, let's just follow that. And at the end, we have what? So there is d of x times the difference between two things. What is this? So this is the average value of ut, that is the temperature. Let's fix t. So this is the average value of the temperature at the neighbors. And what is that? Is the temperature where you are. And so if this is larger than this, that is, if the average temperature at your neighbors is larger than the temperature where you are, this is going to be positive. So the temperature where you are will tend to go up. Right? And if the other way around, if the temperature at your neighbors is less, the average is less than temperature where you are, it's going to tend to go down. So so it's going to smooth. Actually, now this is linear, simple linear algebra to show that this is a system of simple linear differential equation, and it has a solution which is simply the exponential of the matrix t times h. And you can define it two ways, or with this infinite series, or with this limit. So we can show that now, starting with the temperature pi of x, so you don't start with a unique temperature at a given location y, but you start with say a vector of temperature function. This you have one given temperature per vertex, and it doesn't have to be 0 and 1. Then the heat solution, here the equivalent of the convolution is just going to be the matrix product of this matrix, KT and pi. Now we can show that now in our application for languages we're going to have words, and we're going to start with the empirical. So the empirical is a point mass function, so that we can start with values that are positive and sum up to 1. Then we can show that for any time positive, actually what we're going to obtain, so the diffuse version of pi 0, which is kt of pi, is also a point mass function. Start with a point mass function, you're going to end up with a point mass function. And actually you can even show that it's smooth, kind of. That is that if your graph is connected, actually it's going to be strictly positive everywhere. Because just the value where it's 0 will tend to just to go up. And for any t strictly positive, it's going to be true. All right. So there is a Markov chain interpretation. I'm not sure I should. Yeah, I can go through because actually I'm going to use it. So we call that, all right, that you can define KT like that. Now you can look at that. Actually, if K is large enough, you can look at that as just a transition matrix for a simple Markov chain. So let's fix some t positive. Let's choose a large K. And let's define a Markov chain over the graph. So we start with some initial, and the transition is defined by this matrix, the identity plus t over kh.
Excuse me.
Yes.
Is I and h just constants? So what are I and h?
What are?
I
This is the identity.
Is the identity matrix?
Yeah.
And the h is what?
And H is just the matrix, which is just the Laplacian, which is the matrix which is A minus D. And so, for example, for this graph, it's a simple matrix. So you have a 1, 2, 3, 4. So it's a 4 by 4 matrix. All right. On the diagonal, you have minus the degree. So this is 1, the degree is 3. So you have here minus 3. For 2, you have, so minus 2. For 3, minus 2. For 4, you have minus 1. And then you have a 1 each time you have an edge. So there is an edge between 1, 2, 3, and 4. So there is 1, 1, 1. For 2, there is only an edge for 1 and 3. So 1 and 3, and there is a 0 here. And for 3, there is an edge with 1 and 2. And for 4, there is an edge only toward 1. This is the Laplacian of this graph. Okay, so it's a fixed matrix. It doesn't move. And the identity is just the identity. All right? And so this actually defines you a transition. They just expand it. This is what I'm doing here. And you expand it, and it's what you do here. And so, and I take a large K. Why? Because I want this to be a positive number. All right? I want this to be positive, so I have to take K large enough. So if K is large enough, this is positive. So what goes on? I define the transition. I start with distribution pi 0. And if I times 0, I'm at x, I'm going to stay there with the probability that is given here. And I'm going to move to one of the neighbor, okay, with probability t over k for each of the neighbor. So which is the same for each neighbor. Now, it turns out that if I run this chain k time from the formula here, so if I run this chain k time, I'm going to arrive somewhere. There is a probability distribution on where I'm going to be. Okay? And this probability distribution is a nice approximation to kt applied to pi 0 if I start by choosing my point with distribution pi 0. Actually, I show you that because I'm going to use it to compute some kernel in situation where I don't know how to explicitly do this computation. Okay? So I
Right,
can,
the approximation improves as k gets larger.
yeah. Hopefully. No, yeah. All right. So just one word to say, to use that we can somehow generalize that is when you define the Laplacian, you don't have to put the same, you can put different weights, okay? So you can put different weights between your neighbors on the edge. So in what I did, the edge, the weight was always 1, but actually you can take any positive value and same thing, you define you define a new diffusion and you can solve it, and all the properties that were presented before remain true. Just one extension, actually, I'm not going to use it, but it might be useful in some graph.
Before you go on, that function that you had, does it have to be symmetric?
Yeah, because anyway it's defined on edges, it's a non-oriented graph, so it's a symmetric function. It's just you replace 1 by some other.
What is the delta? Is the Dirac?
Is the Dirac. The
Dirac.
delta
And what is
one-
this delta?
Yeah, it's 1 if the property is true, 0 if not.
If there's an edge or not.
So x tilde y means there's an edge between x and y.
Exactly.
Oh, I see. And x equal to y means x is y.
Yeah.
Yes. And then the degree is just the sum of the weight, and not only, like before the weight was just 1. All right? So let me give you some example. There are some examples where one can compute exactly what is the kernel. One example is the complete graph. If you take a complete graph with k vertices, so there is an edge between any two nodes as soon as they are different, so you can compute the kernel. I won't go through that. Actually, you can check that this verify the differential equations that we've seen, and that the initial conditions are correct. And you can check that. If you take I guess a t equals 0, this is 0 and this is just 1, and so this is just delta of x equal y, which is what it should be. And then it evolves, and it's going to evolve, and when t go to infinity, it's going to put the same mass everywhere. It's going to get flat. All right? Now, there are some extension of that. There is a very nice process called graph tensorization that permits to describe the construction on strings. So, same thing, I won't use it, but it might be useful. It's a very nice construction. If you have a graph G1 and a graph G2, maybe I should not do it. Or maybe you will know about that, I don't know. You define a new graph, G, where the nodes are going to be just all the couple, where one element is from G1, one element is from G2. So you're going to take AC, that's one node, and AD, that's one node, and you're going to take BC, it's one node, and then you're going to take BD, that's one other node. And you're going to declare an edge in G, so if you take two things like X1, Y1, so in G, all right? And there is going to be an edge with an X2, Y2, where the X are come from the first graph, the Y from the second graph. So if and only if, there are two possibilities. Or you have X1 equals X2, and then there is an edge between Y1 and Y2, or symmetrically, there is an edge between X1 and X2, and Y1 equal Y2. Okay? So let's see. Here we have A, and C is linked with D. Here we have C, and A is linked with B. Here you have A and D, and here B and D are going to be linked together. And here B are the same, and C and D are linked. And if you continue, you make the product of this graph with, say, G1, you're going to find what? A Q, yeah, sure. And this is the way you build hypercubes. All right? And now it turns out that the kernel, there is a beautiful thing that happens, is that if you have the kernel for G1 and the kernel for G2, it turns out that the kernel for G1, G2, it's just the product. That is KT between, so you have your X1, Y1, and x2, y2 is, so the kt1 between x1 and x2 time kt2, so the kernel for the second graph, between y1 and y2. So you can compute the kernel like that by making just product of kernel, and maybe your graph are simple, and so you can build graph like that. And so, and there is one application is to compare strings. Okay? If you want to compare strings, first you have, and say it's binary string, so this is the most simple things. So in case of binary string, at each location, you have a 0 or 1. And so the graph associated with that is the simplest graph. It's this. And where you declare that, when you declare that a neighbor is, so two values that just differ by this bit. And then you can use this process to define a kernel now on the string by making the product of this simple graph. And so there is an expression for the kernel over strings of length k, and that just turn out to be some function of the Hamming distance between the two strings. And you can extend that. So just want to tell you that there are some special cases where one knows how to build kernels, and many other cases where one has no idea about how to build a kernel,
so
or to compute.
H is here the Hamming distance, not the operator H that you
What?
had before. Is H in this equation is the
Yeah,
Hamming
yeah,
distance,
this is the
not
Hamming
operator,
distance, I'm sorry.
not the linear operator.
Yeah, I should not have understood. Now, there are some diffusion kernels, they are known for closed chain, and it's very nice. It uses some Fourier representation of the chain. There are some known for certain regular trees. All right, it depends where you data. It's known for small graph, because for small graph there is an easy thing you can do.
Bruno,
Yeah.
do us a favor and write over here.
Oh yeah,
Let
sure.
them
Yeah.
worry.
All right. But I'm there, you know.
I know, but
Right,
I
that's
can't
the problem.
I
I'm
can't
the other
leave it
way.
there.
You should have, guys. Another possibility is that you all guys move that way, because I'm there. All right. No, but I won't write that much. But in a small graph, I mean, H, it's a symmetric matrix. All right. So you can write it. You can write it as a diagonal. You can. This is diagonal matrix. You can diagonalize it, and even with a normal basis, so that p minus 1 is just p transpose, and so e to the power th is just p transpose e to the power tg p. All right, and if g is diagonal, the exponential of a diagonal matrix is just the matrix where the diagonal matrix where the elements are just the exponential. So you compute that exactly and you get the kernel. You're done. All right? But now we are interested in large graph. All right? So you cannot do that. So let me give you some application. So some graph we can choose among words.
When you say small graph, what you really mean is that if H can be, you can find its eigenvalues and eigenvectors easily, then you do this, and then you don't need H to be small. If it is sparse, then also you have
All right.
ways to
Fine.
do this.
Yeah.
Right?
Yeah. See what I mean by? I mean that this problem is easy. The case with this problem, but you're right to mention that this problem might be easy in situation even where the graph is huge. All right, and so all right, how can we build some unigram model? So as I told you, so the set of vertices is going to be just a set of words. And we're going to choose the edges, and let's just write what we're going to obtain. So we're going to diffuse. So we're going to obtain a unigram distribution at time t by doing just the matrix product of the kernel time the starting distribution. So I rewrite this by 0, which is like that, and just change the two sums to obtain that, which is the same formula that I put in the board on the board at the very beginning, which is the formula, the kernel estimate. So now let's see what we can do for the kernel. So let's choose the complete graph between words. All right, so we link all the words. As soon as two words are different, we link them. Okay, we start at pi 0. So let's do the computation. I did it for you. So you start with that. What you obtain is the result you had before. And so we expand the sum. So this is just a constant. And in this part, you have just, this is a constant time. So this is 1 over n times the sum of delta of x equal xi, which is exactly the number of times we have seen x in the training set. So you obtain that, and you realize that it's just another at beta estimator. Okay, that you can write with beta is like that, and you can see that when at t equals 0, that corresponds to beta equals 0, so it's just pi 0. And when you let t go to infinity, beta goes also to infinity, and so you're going to get closer to actually the uniform distribution over the graph. So we've just created another at beta estimator. All right, can we do better? All right, this is one thing that I have tried, which is to say, hey, but in density estimation, all the success has come from choosing actually kernels that were data dependent. And so this is one thing we can try is the following. We can say that two words are neighbors if the number of times we have seen them do not differ by more than one. What is the rationale for that? I don't really know. I'm just thinking about the people that I've never seen. For me, they're all the same. The people that I've seen once, all right, they're essentially all the same. Now, the people that I know well, essentially I've seen them a very different number of times, all right? So they are not similar. So let's try that. So computation of the kernel is difficult. Actually, I'm almost on the way to get a straight formulation. But all right, I did some computation with this. So it's in the set of words. And actually, you don't need, so what is the dimension here? So the true dimension of the graph is, so there are 10 to the power 5 words, right? So the dimension of IH is the square of that. However, here, actually, you can cluster things hugely and just cluster all together the word by the number of times you've seen them, all right? And actually, this computation is easy. And I'll show you some result where I've just computed that, so on this reduced graph, and choosing just k equals 3, and choosing one value for t, which is 1 over capital K. I've been just doing some trial and error, and this is kind of the best value, or about the best value I've obtained. And I'll show you some result, and essentially I just tell you the result. It gets better than the good Turing, and gets kind of, no, not better. Better than the at beta, but not as good as the good Turing. But maybe I don't do the thing right, and maybe I do not have the right, the right graph. So let me tell you a little bit about another construction. It is called normalized diffusion, and that was introduced by Majoni and others. I have the reference at the end. So here, you start with the graph, and actually, so you have a set of vertices and a weight function. Okay? So the weight function is going to be, for each couple of vertices, you have a real value, and it's a symmetric weight function. It's, so it's positive, and assumes that it's strictly positive between a node and a vertex and itself. And this is what we interpret as the similarity. So you define locally what is similarity. And then you're going to define the diffusion process, and you hope that this similarity notion is going to extend through the graph. All right, so you define the degree of a node, same way, which is the sum of the similarity. So, but remember now there is an edge from a node to itself. And then you define a Markov chain that way. So the transition is like that. Is you just take the similarity and you normalize it, so that you can check that when you sum over y, this conditional distribution, it gives you d minus 1 of x times the sum over y of the w of xy, which is exactly d of x, so it's sum up to 1. And since all these things are positive, this is always positive, and now the degree must be strictly positive. It's just because W of xx is strictly positive. Okay, so you're all done. But now you have, this is not really a kernel, this is not symmetric for one thing. And, but you can still kind of play the game of, you start with distribution pi 0, and maybe you move just one step according to this transition, or maybe you move k steps. So this is what we do here. So, and we call pi 1, which is the distribution at time 1, and pi k, distribution at time k, which is just applying k time the same thing. And now, if you let it go, actually what you show is that, so you need that the G to be connected, and then you go to a distribution which is like that. So for each node, there is for each word, if you want, for each vertex, there is a weight which is proportional to the degree of this vertex. Okay, so which is this degree, the degree of this vertex, divided by the sum of all the degrees in the graph, so that is sum of 2.
So this is essentially a random walk on the graph. And
This is a random walk on the graph, but it's not, there are weights that makes that. It's not just one everywhere. Okay?
And this is the stationary distribution that you're
And
showing.
this is the stationary distribution. And so let's, so in the example, we're going to have a training set. We start with this pi 0, and same thing, let's just rewrite where we're going to be at time 1. This is the formula. So this is very similar. This thing played the role of the kernel, all right? But it's not a symmetric kernel, it's just another one. So let's do an example. So we have k word in our vocabulary, we have all words, and we're going to define the weight as follows. We're going to have the weight 1 between any two words, and we're going to add some quantity, say alpha, in the case where a word from, on the edge of a word to itself. So on this edge, actually you have 1 plus alpha, and then on all the other one, you have just 1. So, like it says that a word is slightly more similar to itself than to any other, but then it's similar the same way to any other. Why not? All right, so you can do the computation exactly, it's easy, and you end up with what? Name it another at beta estimator, okay? Okay, with another parameter that you can link with alpha. Now, can you do differently? Yeah, you can choose, so a similarity with kind of the same idea that we've chosen before, all right? So W of xy, same thing. We're going to choose 0 or 1s, and we're going to choose 1 if the number of times you have seen the word x differ to the number of times you have seen the word y by less than 1 count. So then you can compute the degree, and hey, there are these numbers that begin to appear. So that's, I recall you, the degree is the sum of all y of this quantity. Right? So this is why what comes up is the number of words that you have seen. Actually, it should be n of x here. Number of words you have seen, n of x minus 1. Number of words you have seen, n of x plus 1. Begins to look like good Turing a little bit. And then we can write down exactly what is the distribution at time 1, and you find something like that. Okay? And how can you compare it to good Turing? For example, you can look at the mass assigned to the word that you have not seen. This is what we do here. So assume n of y equals 0. I have to until 5:30. Am I right? Okay. For this word, so by I of y, from this formula you get this. There is just one element in the sum for which the one for j equal 1. So you obtain that. And if you sum over all the words y's that have not been seen, you obtain this formula, which is just this time R0. So you can rearrange this like that, and you can see that when R0 is large compared to R1, that is the number of words you have not seen is large, you get something which is similar to the good Turing. The good Turing gives you just R1 over n. Right? Okay, so that's another example. So I'd show you some quick experiment I've done, and I thank Damianos for having prepared the data for me. So we used the UPenn tree-bound corpus. So there is one section, 10 to the 5th word for testing. We split the training set into 10 subsets, leading to 10 data sets of size about 10 to the power 5 tokens each. We look at the code lengths that we achieve on the test set. We show mean code lengths and standard deviation were available, and we've chosen this value for k in the result below. So this is a typical things we obtain. So let's start, whatever, they're about the same. So this is a training set of size 10 to the power 5. This is the good Turing, so the mean code length is 1068, and this is the standard deviation. So this is the add beta with beta equal 1, 11.1. And so these two values are the two estimates I've shown you. So this one is the one for normalized diffusion. So it's very close. 10.69, if you look at what the standard deviation is, the standard deviation is very large compared to all the differ. All right? So it's still larger, but they might not be significantly different. And then the one I obtained for now with the kernel diffusion is slightly larger. Okay? Also, I'm not done with that. I might get a way to get a better result. I'm not even sure exactly where to stop. I'm not sure I compute enough. And these are similar, the result for the larger training set. So it's actually less. We don't see as much because they get closer, because the size of the training set increase. So this is the good Turing, and these are the two I presented to you. But even if it's like that, I think these two are very close, and but still, the one with the kernel get a larger code length than the good Turing. But still,
remind me again, which is the normalized? Which is in the normalized diffusion, you have this thing where a word is similar to itself and a little more similar to itself than to any other word.
No, actually.
Which is which? Yeah.
No, actually, in what I've chosen, this is this graph. So
Okay.
actually, what happened is that all the words that are seen the same number of times are linked, and you are as similar to yourself as to any word that has been seen the same number of times, or one less or one more.
Okay.
So there is nothing particular. Actually, we could add, if we want in the kernel, we could wait a little bit for each word that he likes himself a bit
Right.
more than the other one.
So this is what you mean by normalized diffusion.
And this is the normalized diffusion framework.
And then there was another KD. Which one is that?
And the KD is the one I presented before, so which is the one from the heat equation.
Okay.
The one from the heat equation with the edges of the graph defined by the same formula. But the evolution is not the same, and it's not giving the same thing. But and there is one parameter here on when to stop, and if we want on the other one, there is no, or we just say that we stop at time 1, we just make it 1. So the parameter is 1, all right? Okay, and finally, I just want to tell you that if you're interested in these things, and there is much more that can be done using kernel on graph, and in particular, it opened the way to do all the computation, the statistical computations that are done in metric space, like a PCA, like support vector machines that are defined on metric space. Actually, this kernel, they define a scalar product. They are positive definite, but it was not the subject of my talk. But there is much more that can be done with this kind of two tools that I presented. One, the diffusion from the heat equation, and the other tool are this normalized diffusion. So just some reference if you're interested. So most of the material on discrete graph was from this paper, and John Lafferty will be with us in 1 week, I think, or 2, in 1 week. And then there is this work by Maggioni, Kaufman, and Salam. Maggioni was in the applied math during the autumn. And I hope that one of these guys, there is also a guy at Google now, Stéphane Lafont, who was with them and is doing great stuff. And a little experiment you've been studying in model appear in these things that is unpublished for now. And I would like to thank you very much for listening to this.
Yes, you have to tell us more about this graph structure and how it affects your diffusion. Like with the words, you had these simple notions of neighborhood, where it was all defined by counts.
Yeah.
But do you have a sense for what else could be done?
All right, so I actually begin to think about it. At first you might say, hey, but why not use some real similarity between words? I mean, some grammatical. And certainly it's a way to go. So you have certainly some care. There is some care. You cannot do anything. Why cannot you do anything? Because you need to be able to compute. That is, just the K is the matrix, and you need to be able to store it. Okay? And if it's not sparse, since it's defined, okay, so it's defined on the set of words that you've seen, square. This is the number of entries. So it's big. And so certainly you would prefer to have some kind of sparse matrix to be able to do the computation. But then, yes, I mean, I think that it's very open, and the way to choose this graph, so in the first case, or in the second case, the way to decide what should be this graph, what are the kernels, it's certainly totally open. I have no idea what is the right way to go, but certainly you have the idea you could incorporate many, several kind of information.
I mean, it seems like the big problem is that you want it to be sparse, but you also want it to be connected. If it didn't have to be connected, it'd be very easy to
you don't have to be
threshold
connected.
areas.
You don't have to be connected, in principle.
But if you're not, you don't get any.
If you're not, you don't get any. Right.
Well,
You,
I mean, if
each-
No, it depends where you start. If in each connect component you
Yes.
start with non-zero mass, you're going to diffuse it. Surely if you put all the words that you have not seen together and you just leave them together, and you do not connect them,
If
they
you don't
go...
have any edges, you get no smoothing. David was saying you want to have some edges, so you get some smoothing, but you also want it to be sparse.
Yeah, exactly.
right, but right. As long as you can connect words that you haven't seen to other words that you have seen, then you'll get some.
Yeah, you get some
bounce around.
smoothing happening. Also, you could start with another distribution. I start with the empirical. Why? You know, maybe someone has a better idea. Yes?
So, of course, we can make up random formulas for smoothing, and you know, some of them would do well and some of them would do poorly and so forth. So, ordinarily, I want to try to justify picking a particular smoothing formula as a statistician in terms of saying, well, there's some real distribution. I have a sample from the distribution. Maybe I have a prior over distribution, and I would like to make some decision theoretic appropriate choices. So I can justify good Turing on that basis by saying that if all words that have the same count must have the same probability, then the good Turing formula maximizes the probability under leave one out cross validation. So that's a reasonable justification. It happens to be non-parametric. I didn't have to make any assumption about I didn't need to assume any prior over distribution.
Yeah, but it's not exactly true. For example, I mean, when you look, it's almost true. I know the work on good Turing. There are many things, but it's almost true. But for example, how do you justify that you have to choose this M? It doesn't come into, that for large M.
Well, that's not part of good Turing.
What?
That's the M is actually not part of good Turing. That's part of Cat's back off. Which
Yeah,
is
but
a
I mean, if
modification
you
on
use-
good Turing that gets used because good Turing is unstable for certain reasons that we can talk about.
Exactly.
But
So
what
it's
I'm-
not really understood. I mean, all right. Okay,
Well,
let me
no,
finish the
that's-
question.
But that's not my question.
Yeah.
My question is, suppose I'm a statistician. How do you convince me that a diffusion kernel has anything to do with predicting the future? which is what we're trying to do here.
Okay, okay. So you might want to ask this question first in the case where it's used now, which is for density estimation. And actually, a lot of statisticians have been, I not be very convinced by this kernel estimate because for some reason it's not constructed from ground principle. Now you can show in some circumstances, okay, so what are the results for kernel density estimate? There are some results with some cost function, and you can set up some optimization problem and show that they minimize some kind of risk over a large set of functions. There are some results that are even non-asymptotic, that are a bit complex to say with parameters that you cannot compute, but there are justification for choosing a kernel estimate in the situation of density estimation.
So
Now,
you mentioned risk minimization, which is definitely a way to justify that you want to use one smoothing formula rather than another. The other way is to have some priors. And so you would pick a smoothing formula if the risk that you're trying to minimize is not perplexity but something else.
Well, the
so are you saying
comes
this
in the expectation you're using to compute the risk.
Are you? They both come in. I'm saying that you could, if you manipulate either, it'll motivate a different smoothing formula. So are you saying that in these theorems the graph structure is somehow encoding some kind of risk function? It would be.
So what would be the equivalent? Yeah, I have no idea about that. I haven't thought about it yet. If there would be some kind of equivalent of the optimality kind of the theorem you can obtain in the continuous case, if you could, maybe obtain some equivalent in the discrete case. I have not looked at it.
So tell me again, what is this result which says that under some conditions the kernel density estimate is optimal? Well, how does that result go? I don't know this one.
All right. There are several of that. Now you have to set up a cost function. I don't even remember exactly.
Okay, I'll ask you about this afterwards because
I
it's something I don't know.
Yeah.
I think one of the things I think when you're going from the heat diffusion to the discrete case is that in the heat diffusion case you have a natural definition of neighborhood, which means there's a physical law says if this particle has a temperature this, then the next one couldn't be too far away.
Yeah.
So that's the underlying structure there.
Yeah.
But when you go into the discrete case, it's not easy to define such an analog between words. So then, like what you have done, you ended up using the n of x minus n of y is equals n1. And that's a crude approximation. I think that's why this analog works.
But that's also the richness of the thing. It lets you, some maybe too much room, but it's good to have room. So to define yourself the graph that you think is meaningful, and then just run it. But it's true. And in all these methods that's open, then now what you do is defining your graph and your weights. There is all engineering there that this method do not permit you, they do not just give a result, but they let you use a lot of engineering to define your graph. But then when you've done, you can use these techniques and make some sense, I think.
Okay, thank you.
Thank you.